The enigma of whether the universe is infinite is a pondering inquiry that permeates the minds of all cosmologists, and undoubtedly, it has crossed your thoughts as well. Initially, the answer may appear straightforward, an affirmative nod to the infinite expanse of the cosmos. However, dear traveler, let us delve into the intricacies of this question and scrutinize whether this seemingly boundless universe truly lives up to its reputation. Today, we embark on an odyssey to explore the farthest reaches of the cosmos, unearthing the mysteries of distant worlds. But, before you set forth on this cosmic journey, I implore you to express your appreciation by liking this video and subscribing to ensure you don't miss any revelations. Thank you. And may your cosmic sojourn be nothing short of extraordinary. The assertion that the universe is infinite might leave you astounded, yet the reality is, we may never attain a definitive answer. Theoretically, the question of the universe's infinity proves elusive. While the theory of general relativity adeptly narrates the universe's evolution from its inception, it remains silent on the subject of its geometric properties. Einstein's relativistic theory of gravitation merely asserts that the universe's curvature is zero. But what does this zero curvature signify? Let's envision 3 points in space-time and connect them. In the absence of curvature, we don't form a pyramid but a triangle, a flat object indicative of a universe without curvature, and hence, infinite. Diverging opinions among cosmologists persist. To gain a deeper understanding, let's scrutinize the 3 potential curvatures of the universe: closed, positive spatial curvature; open, negative spatial curvature; and flat, zero spatial curvature. In an open universe, boundless and continually expanding, its mass lacks the magnitude to impede this expansion. Conversely, a flat universe, though infinite and destined for perpetual expansion, possesses sufficient mass to decelerate this expansion to near zero, albeit over an infinite timeframe. In a closed universe, mass surpasses the threshold to halt expansion, creating a finite yet edgeless universe that, akin to a sphere, contracts once expansion ceases, leading to a cosmic collapse. In 2019, the theory of a flat universe faced scrutiny when data from ESA's Planck Space Telescope hinted at the universe's potential finiteness, taking on a spherical shape with a positive curvature of 4%. This departure from previously established data challenges the cosmological model, suggesting a finite and spherical universe. The basis for this hypothesis lies in an image of the cosmic microwave background, captured by the Planck telescope between 2009 and 2013. This image reveals gravitational lenses, optical distortions caused by high mass densities, providing insights into the density of matter in the universe. According to the theory of relativity, when density exceeds 5.6 atoms per cubic meter, space assumes a spherical shape. Despite debates among cosmologists, this discovery prompts further investigations to settle the matter definitively. The observable universe, a mere fraction of the whole, is finite. Its finite nature arises from its finite age, determined by the time elapsed since the Big Bang. While the universe's existence pre-Big Bang remains a mystery, current cosmological models falter at describing matter's behavior in such extreme conditions. The universe's age, established in 2020 at 13.77 billion years with a margin of error, dictates the observable universe's boundaries. Defined by a sphere of 13.77 billion light-years, the observable universe's size is constrained by the cosmological horizon, centered on the observer, our position being Earth. However, this constitutes only a minuscule fraction of the entire universe. To discern the universe's infinitude, we must fathom its curvature. Thus, our certainty about the universe's infinity remains elusive. Yet, together, we shall embark on an exploration of the observable universe, unraveling its discovery, theorization, dimensions, and the celestial entities it encompasses. Fasten your seat belts for a captivating cosmic journey. And so, the journey commences, accompanied by the harmonious tones of the cosmos. The observable universe, as elucidated in cosmology, is the segment of our vast cosmos that lies within the purview of our perception. As previously expounded, this observable universe is not boundless. Its confines are encapsulated by what is known as the cosmological horizon. This horizon serves as the threshold, delineating the extent of the universe observable from a specific vantage point, typically the Earth. The cosmological horizon isn't solely limited to the realm of visible light. It extends to encompass the boundary from which various forms of signals, including electromagnetic radiation, gravitational waves, or neutrinos, can either be emitted or received. Furthermore, it serves as the demarcation line between the observable universe, comprised of objects whose emitted light has traversed a journey of less than 13.7 billion years, and the imperceptible expanse whose galaxies remain too distant for their light to have reached us. However, portraying the cosmological horizon as a static 13.7 billion light-years away is a simplification. The dynamic factor of the universe's expansion must be considered. When this expansion is factored in, the photons emitted by the cosmological horizon exist beyond the 13.7 billion light-year mark. This is due to the universe's expansion outpacing the speed of light. In reality, the furthest signals reaching an Earthbound observer emanate from the cosmic microwave background, an omnipresent radiation filling the cosmos. The region of emission, known as the last scattering surface, lies at the outer limits of the observable universe. Cosmological models posit that, owing to the universe's expansion, this last scattering surface is now situated approximately 46.5 billion light-years away. The portrayal of the observable universe often manifests as a sphere, with Earth positioned at its center. This is not an endorsement of geocentrism, an antiquated model that deemed Earth stationary at the universe's epicenter. Rather, it is a relative concept, acknowledging that observers, situated on Earth, perceive this observable universe. Observers elsewhere in the cosmos would have a distinct observable universe, yet the radius of this sphere remains constant. The observable universe's definition is tethered to what is perceivable and measurable. As time unfolds, our ability to observe extends further into the cosmos. The visible radius expands incrementally, analogous to the progression of seconds or years. With each passing second, we traverse a new depth of space equivalent to 300,000 kilometers, mirroring the speed of light. Over a year, our exploration encompasses several new galaxies. Objects at the farthest reaches of the observable universe are scrutinized in their primordial state, providing glimpses into the ancient epochs of cosmic evolution. Embarking on the exploration of the observable universe brings us face to face with intriguing phenomena. Objects situated billions of light-years away hold a particular allure, for they represent entities whose light has traversed the most extensive cosmic distances to reach us. The phenomenon of redshift, a consequence of the universe's expansion, accentuates the further afield these objects are, the higher their redshift becomes. This is a pivotal aspect of comprehending the observable universe. Central to our understanding is the cosmological principle of homogeneity and isotropy, one of the four foundational principles in cosmology. These principles serve as indispensable simplifying hypotheses, allowing us to grasp the vast scope of cosmological phenomena without delving into the intricate details of particle velocities and positions across space. The principle of homogeneity asserts that the universe exhibits spatial uniformity, irrespective of the observer's position, aligning with Copernicus's principle that refutes geocentrism. Additionally, isotropy posits that the observable universe looks the same regardless of the direction from which it is observed. Visualizing the observable universe as a sphere, with the Earth at its center, emphasizes the relative nature of our observational standpoint. Although certain regions remain beyond our visual reach, such as those obscured by black holes, the observable universe remains a comprehensible construct. Stellar black holes, formed from the gravitational collapse of massive stars, differ from supermassive black holes found at galaxies' cores, which continue to be subjects of active research into their origins. Yet, the inability to observe certain regions does not negate their existence, as contemporary theoretical models offer insights into the entirety of the universe, even if our observational lens captures only a fraction. Despite these comprehensions, navigating the observable universe introduces its share of complexities. The concept of look-back time underscores that, even though we observe the observable universe, we perceive it not as it is in the present, but as it was at the moment of observation. This temporal discrepancy is crucial for interpreting the age of astronomical objects, calculated by estimating the time since their emitted light reached us. A case in point is the primordial galaxy HDF 850.1, situated at a redshift of Z equal to 6.5, suggesting a look-back time of 850 million years post-Big Bang. The challenges persist as we grapple with the inherent difficulties of discerning distances in cosmic terms. Spectral line shifts aid in gauging redshift, but converting this into cosmic time is contingent on the chosen cosmological model. Furthermore, distinguishing between the reception distance, where the object appears to us, and the emission distance, where it was at the moment of light emission, is essential. The latter is closer to us due to the expansion of the universe. Visibility poses another challenge, with objects growing less discernible and energetic the farther away they are. This phenomenon contributes to the finite nature of the observable universe, as beyond a certain distance, objects elude observation, ceasing to be part of the visible cosmos. As the universe expands, the dynamic interplay of distances among celestial entities within the observable universe introduces fluidity to its boundaries. Galaxies annually transition from visibility to invisibility, while new galaxies come into view, creating a perpetual cosmic spectacle. In the grand tapestry of cosmic exploration, these challenges weave a narrative of complexity and wonder, urging us to fathom the intricate dance of space, time, and light in our observable universe. As our journey takes us further from the epoch of the Big Bang, our observations paint a captivating picture. The cosmos, comprised of individual celestial entities like supernovas, stars, and galaxies, appears to exhibit a phenomenon, a seemingly expanding dance where these entities move apart. Contrary to intuition, this is not attributed to an acceleration in their movement speed, but rather to an accelerated generation of space between each galaxy. The expansion of the universe is encapsulated by Hubble's constant, a parameter denoting not a literal duplication of space, but its continual expansion. With an approximate value of 70 km per second per megaparsec, this constant elucidates that, on average, for every megaparsec of distance separating 2 points in the universe, these points are diverging at a speed of around 70 km per second or 43 meters per second. Therefore, it describes the dynamic relationship between the speed at which 2 points move away from each other and the distance between them, rather than an addition of new space. This complexity does not stop here. There are additional parameters that warrant consideration to fathom the inner workings of the observable universe. The universe, as we initiated our exploration, is approximately 13.77 billion years old, or for simplicity, 14 billion years. While one might be tempted to assert that the size of the observable universe is 14 billion light-years, reflecting the age of the universe, the reality is more intricate. Due to the expansion of the universe, the origin of light particles emitted by distant objects has shifted further away from us since their initial emission. To discern the geometric distance at which these distant objects, whose light we perceive 14 billion years later, are located, we must delve into a cosmological model. Using the speed of the universe's expansion, we can deduce the distance these objects have traversed since the photons were emitted. Based on current cosmological models, the estimated radius of the observable universe today is around 46.5 billion light-years. This renders the observable universe as a sphere centered on Earth, with a radius of 46.5 billion light-years or 450,000 billion kilometers. The diameter of the observable universe is thus approximated at 93 billion light-years. An intriguing observation is that theoretically, we can only observe objects up to the distance of the cosmic microwave background, around 380,000 years after the Big Bang. At this juncture, the universe had cooled sufficiently for electrons to join atomic nuclei, liberating photons and light that had previously been ensnared in a fog of matter. This liberation facilitated the survival of photons long enough to reach Earth and be detected by our instruments. A pivotal moment in this context is the discovery of the Compton effect, also known as Compton scattering, by Nobel Prize-winning physicist Arthur Compton in 1923. This phenomenon, arising from the collision between a photon and an electron, demonstrated that light is a tangible particle characterized by energy and momentum. It revolutionized our understanding of light, transitioning from a solely wave-like description to acknowledging its particle nature. Returning to the epoch 380,000 years post-Big Bang, theoretically extracting information from this early period, prior to the universe cooling enough for photons to reach us, would necessitate detecting gravitational. Venturing deeper into the complexities of the observable universe unveils intriguing facets, including phenomena yet to be fully comprehended, such as gravitational waves or elusive fossil neutrinos. It's crucial to differentiate between the size of the observable universe, confined by the cosmological horizon, and its geometric size. This distinction is pivotal in deciphering seemingly paradoxical observations, like the ability to witness a galaxy positioned 16 billion light-years away, despite the Big Bang occurring only 13.7 billion years ago. In this case, the 16 billion light-years denote the geometric distance, accounting for the universe's expansion, while the light reaching us today might have originated from a location just 10 billion light-years away when scattered. Moving beyond the spatial nuances, the mass of the observable universe beckons our attention. Employing various methods, scientists estimate the quantity of matter within the observable cosmos to be on the order of 10 to the power of 80 atoms. Often framed in terms of density and energy, the universe's composition is predominantly matter and energy. The age of the observable universe, a recurring theme in our journey, is pivotal in unraveling cosmic mysteries. Recently estimated at 13.77 billion years, with a margin of error of 40 million years, this finite age delineates the time elapsed since the enigmatic initiation of the Big Bang, marking the advent of space-time. This estimation is grounded in data collected by the Atacama Cosmological Telescope in Chile between 2013 and 2016, corroborated by measurements from ESA's Planck Space Observatory from 2009 to 2013. This revised age carries implications, notably that light from a cosmic object cannot have traversed more than 13.8 billion years. The most distant objects detected at the observable universe's edge took precisely this duration to reach us. The co-moving distance, covering 13 billion years, reflects the space between us and the farthest point in the observable universe. However, the geometric distance, factoring in the universe's expansion, stretches to 46.5 billion light-years. Armed with knowledge about the age, size, and mass of the observable universe, we recognize the intricacies of studying a dynamic space with ever-shifting boundaries. Now, we embark on a journey into the heart of the observable universe, exploring its cosmic constituents. Let's initiate this exploration by examining the organized structure of the observable universe. Argentinian artist Pablo Carlos Budassi has crafted a remarkable, detailed map of the observable universe, cleverly presented in the form of a sphere, showcasing its various layers. Utilizing a logarithmic scale and working with astronomical data from Princeton University, this image provides a breathtaking snapshot of the observable cosmos. The observer, stationed on Earth, finds the solar system at the center of this cosmic sphere. The Sun, accompanied by the planets of our solar system, Mercury, Venus, Earth, Mars, Jupiter, Saturn with its majestic rings, Uranus, and Neptune, are visible. The Moon orbits Earth, and the asteroid belts, namely the Kuiper belt and the Oort cloud, appear as rings of cosmic dust. Extending between 30 and 55 astronomical units beyond Neptune's orbit, these belts contribute to the intricacies of our cosmic neighborhood. As we delve deeper into the cosmic tapestry, the celestial neighborhood expands to reveal intriguing structures beyond our solar system. The Kuiper belt, akin to the asteroid belt but more expansive and massive, harbors small bodies and 3 known dwarf planets, Pluto, Makemake, and Haumea. This region, formed alongside our solar system 4.6 billion years ago, extends 20 times wider and 20 to 200 times more massive than the asteroid belt. Dutch-American astronomer Gerard Kuiper's prediction of the Kuiper belt's existence in 1951 marked the beginning of its acknowledgement, with the first discovery in 1992. Extending beyond the Kuiper belt lies the Oort cloud, a hypothetical and unobserved sphere consisting of frozen comets. Conceived by Dutch astronomer Jan Hendrik Oort in 1950, the Oort cloud is posited as the reservoir for long-period comets, spanning distances of 20,000 to 100,000 astronomical units from the Sun. While its existence remains speculative, scientists propose its presence to explain analyses of comet orbits. The Oort cloud's icy composition, including water, methane, and ammonia, suggests a formation closer to the Sun, later scattered by gravitational forces during the Solar System's infancy. Venturing outside our Solar System, the Alpha Centauri star system emerges, situated 4.37 light-years away. Comprising 3 stars, Alpha Centauri A, Alpha Centauri B, and Proxima Centauri, the system stands as the closest to our Solar System. Proxima Centauri, a red dwarf, is particularly noteworthy as the nearest star to us for around 32,000 years. Proxima Centauri B, an exoplanet in the habitable zone, beckons interest despite challenges, such as its star's intense radiation and potential gravitational lock. Proceeding on this cosmic journey, Pablo Carlos Budisi's representation reveals the Perseus arm of the Milky Way, our home galaxy. A spiral galaxy, the Milky Way's exact structure remains elusive, modeled through methods like 3D mapping and parallax measurements. The Perseus arm, one of the Milky Way's 4 primary arms, may be more dispersed than initially perceived. Within the cosmic neighborhood lies the local group, a collection of over 60 galaxies spanning 10 million light-years. Dominated by the Milky Way and the Andromeda Galaxy, M31, the local group harbors a fascinating future collision between these 2 giants. Expected in 4.5 billion years, this collision poses minimal risk to our solar system, leading to the creation of a new mega-galaxy with a supermassive black hole. Andromeda Galaxy, or M31, stands out as one of our significant cosmic neighbors. Larger than the Milky Way, it boasts around 1,000 billion stars, 25% more luminous than our galaxy. Positioned 2.55 million light-years away, Andromeda has captivated astronomers for its luminosity, though its star formation rate and supernova count may impact its future radiance. As of 2016, the Observable universe houses an estimated 2,000 billion galaxies, unveiling a vast cosmic tapestry previously underappreciated. Researchers, leveraging Hubble Deep Field images, converted them into 3D representations to unveil the evolution of galaxy density inversely correlated with the universe's age. This discovery prompts questions about the evolution of the universe and the role of galactic mergers in shaping its current state. The study also emphasizes the tendency of galaxies to cluster, forming structures like superclusters. Examples include the local group, the Virgo cluster housing 132,000 galaxies, and the Hercules corona borealis Great Wall, one of the largest known structures in the cosmos, spanning around 10 billion light-years. As we venture deeper into the cosmos, the scale of celestial structures grows exponentially. Galaxy clusters, more massive than galaxy groups, contain abundant hot gas. The Virgo supercluster, with the Virgo cluster at its core, stands out as one of the superclusters of galaxies, stretching hundreds of millions of light-years. Superclusters, the largest cosmic structures, play a crucial role in understanding the universe's expansion. The redshift or blue shift, observed on the scale of superclusters, provides insights into the movement of objects relative to us. Within the Virgo supercluster, our local group finds its home, marking it as the local supercluster. Approximately 65 million light-years away, this supercluster is notably dim, leading scientists to theorize a significant presence of dark matter. The Hydra Centaurus supercluster, comprising the Centaurus and Hydra superclusters, holds fame for housing the Great Attractor, a mysterious zone influencing the convergence of the local group and the Virgo supercluster. Beyond these, other superclusters dot the observable universe. The Shapley supercluster, located 650 million light-years away, beckons attention for its size and luminosity. Its 25 galaxy clusters, containing a myriad of galaxies, contribute to the ongoing exploration of cosmic structures. The Perseus-Pisces supercluster, recognizable by its extended, dense wall of galaxies spanning almost 300 million light-years, contains the Perseus cluster, one of the most massive galaxy clusters within 500 million light-years. The Hercules supercluster, named after the constellation Hercules, unveils its interconnected superclusters dominated by rich galaxy clusters. Moving closer to Earth, the Hercules and Corona Borealis supercluster, also known as the Coma supercluster, stands as the closest supercluster at 300 million light-years. Renowned clusters within it include the Coma cluster and the Leo cluster. Superclusters not only aid in understanding the universe's expansion, but also provide insights into the organization of matter. Researchers have observed a non-uniform distribution of superclusters, revealing vast gaps between these structures, emphasizing that over 90% of the universe comprises empty space. Among these voids, the Bouvier void, adjacent to the Shapley supercluster, holds significance. Despite its name, it doesn't indicate complete emptiness but rather a region with significantly less matter. Voids like these are believed to have grown from small irregularities in the early universe. Expanding our view, we encounter larger structures like the Laniakea supercluster, which houses the Milky Way and Andromeda galaxies. Further, the Shapley supercluster paves the way to the Hercules and Corona Borealis Great Wall, an immense structure measuring 10 billion by 7.2 billion light-years. Notably, the Great Wall contains several thousand galaxies, including the Hercules and Corona Borealis supercluster, discovered in 2013. Venturing to the very edge of the observable universe, the Great Wall marks one of the largest structures known. Stretching 10 billion light-years by 7.2 billion light-years, it surpasses previous records set by structures like the Sloan Great Wall. The complexity of the cosmic web emerges, illustrating the interconnected filaments of galaxies. As we approach the cosmic microwave background, CMB, on the edges of the sphere, we encounter the universe's remnant radiation from approximately 380,000 years after the Big Bang. The CMB, also known as fossil radiation, is a diffuse glow present throughout the observable universe. The final layer of the sphere reveals a ring of quark-gluon plasma, representing the cosmological horizon. This plasma, existing at extremely high temperatures and densities, is akin to a soup of quarks and gluons. It holds significance for understanding the early moments of the universe. Pablo Carlos Budisi's representation encapsulates the vastness and intricacies of the observable universe, from superclusters to voids, and from ancient cosmic background radiation to the mysteries at the edge of our cosmic understanding.